Welcome back to Introduction to Material Science Engineering. This is the second of two recorded lectures on material failure. In the first of our two, we went through some fracture mechanics and criteria for fracture, defined K1C, and we explored the difference in energy absorption mechanisms for both ductile and brittle fracture. So now we're going to move into high-rate fracture toughness testing, which is basically the quick and easy semi-quantitative means of assessing fracture toughness of materials when you don't have time to do the very intensive repetitive testing necessary to establish a true K1C. And then we will address creep and fatigue, which are two more insidious means of material failure that ultimately results typically in fracture or ductile overload. Okay. High-rate fracture toughness testing, or high-rate toughness testing. This is an easy comparative test of fracture toughness mainly for different materials or for the same material tested at different temperatures. So we'll measure energy absorption at high strain rates. This is actually a true energy balance method in the case of both Sharpie and IZOD. It's a very old and elegant test. There's no stress intensity geometry factor to calculate. These are standard test sample geometries, and so we don't have a Y factor. And we can't use it, unfortunately, to directly estimate design stress or tolerable flaw size. So that's the downside. We can't use it as design input. But if we have a material that we know works in the design, that we know perhaps even conforms to a given safety factor, then we can use this test for comparison for other materials that might be just as good or better. And certainly we can preclude materials that wouldn't work. And last but not least, especially for our body-centered cubic metals, we can identify something called ductile to brittle transition temperature. And you can see on the picture below of the ship literally cracked in half. This was not photoshopped. This is a real picture. It's one of the old Liberty ships, or one like it. And this was a steel ship that failed due to a ductile to brittle transition, and then failed literally, probably unfortunately, in service. Many of these sank in service. So starting with Sharpie and IZOD impact testing. So in these, we just literally use an energy balance. We take a notched sample and we fixture it underneath a weighted pendulum in a special test fixture. The samples are notched to give a stress intensity or a stress concentration factor. We elevate the weighted pendulum to a certain height, release it, let it swing under gravity. It whacks the sample and then rises over on the other side, and so we can convert the potential energy of the weight of the hammer times its height times gravity, subtract the height that it attains on the swing, the upward swing after it contacts the sample, and the difference in the two is the energy absorbed by the sample. And again, it's a comparative test, but it is a direct test of energy absorbed. And so if we do this at different temperatures, we can compare the energy absorbed by a material of the same sample configuration. Again, we have to machine it and make sure that the sample size and geometry is the same. And these again are typically set by ASTM standard. So there's plenty of instructions on how to keep the test parameters constant. And so we can get a comparison material to material and material at a given temperature. And these are the types of results that we typically get. So if we plot impact energy, which again is the difference between the original height of that pendulum to the final height, versus temperature for given materials, we can see that, for instance, face-centered cubic and hexagonal close packed, even though hexagonal close packed is not very ductile, it can still absorb quite a bit of energy on impact. Those tend to stay reasonably high over a wide range of temperatures. Your higher strength materials, heat-treated steels, some of our more brittle composites, ceramics for instance, are going to be low at any temperature. That's not surprising. That's what we would expect just from general fracture behavior. The blue curve is the one that is important from the standpoint of ductile to brittle transition, and this is very characteristic of low strength steels and other room temperature ductile body-centered cubic metals. At a reasonably high temperature, room temperature down to ordinary service temperatures maybe, they have very high impact energies. But below a certain point, the fracture toughness drops dramatically, and they'll have very, very low fracture toughnesses below that, characteristic maybe even as low as a ceramic, or certainly characteristic of a very low toughness metal. And if that range is encountered in service, you can end up with a material that no longer meets your fracture toughness requirements and could fail in service, just like those ships. So that really happened, and it's unfortunately something that happens reasonably frequently. This is akin to the type of transition we see at glass transition in a polymer, where we go from something that's rubbery or fairly tough, possibly even viscous, to something that's very rigid, except in the case of our BCC metals, it's always rigid above and below, but we have a dramatic drop in fracture toughness. Something to remember for ductile to brittle transition is it's quite specific to body-centered cubic metals. So if you want to avoid the ductile to brittle transition, or otherwise known as D to B transition, you'll design with a face-centered cubic material. And that's one of the reasons that face-centered cubic materials tend to be widely used in cryogenic applications, is we don't have to worry about a sudden temperature-induced loss of fracture toughness. There's other problems with face-centered cubic materials that we'll see in fatigue, but from ductile to brittle transition standpoint, they definitely have an advantage. So fatigue, this is one of our difficult to predict, or they're predictable but difficult to inspect types of failure. This is something that's somewhat feared simply because it's what we would consider insidious. You can have a material that is subject to cyclic loading, for which we will get failure at stresses well below yield. So this is a fracture-related type of failure, and it's something that is very difficult to inspect for. You would have to inspect for flaws the way you would looking for your A for your K1C calculation. So it's a very expensive type of inspection to detect. So it's basically defined as a crack propagation due specifically to cyclic loading. And again, the big problem with this in terms of designing materials in service is that the cyclic loading can include a range of stresses, amplitude of stresses, that are well below yield. So if you have a material with a yield strength of, say, 30 ksi, you can have a cyclic loading that varies between, say, 0 and 10 ksi, and have that drive a fatigue-related failure that can cause a low-rate crack propagation that will ultimately grow a crack to the size that it will exceed the K1C given your applied design loads. So you can think about fatigue as a way, as being working in tandem with what we've learned about fracture, and being a way that you're growing that A, the crack length, given a certain applied design stress to the point where you then exceed K1C and you fail by catastrophic failure and spontaneous crack propagation. So there are some defined characteristics of fatigue that allow us to understand it and then basically design to preclude it. Something to, again, be cautious of. This is in fact responsible for about 90% of mechanical failures. So if we don't have corrosion, we don't have a high temperature creep situation, or an environmental assisted cracking, chances are fatigue was what was the initial cause of the failure. The material will ultimately fail by spontaneous crack propagation once you grow that crack to beyond K1C, but it will probably be growing by fatigue. This happens across all classes of materials. Nothing is immune. Polymers, ceramics, metals, they all have it. We'll see in the case of metals, there's again a difference in face and body-centered cubic, with the face-centered cubic materials not having what we call a fatigue limit, but they can still they're still subject to fatigue. Okay, what is cyclic loading? It's effectively just stress that varies with time. And the key parameters that we will have with respect to that are the average stress, sort of the mean point about which the stress varies, and then the stress amplitude. So you can see over in our diagram on the right, if we have a sinusoidally varying stress, cyclic stress, sigma m, the mean stress, is just literally the average, and then the red arrow with the capital S is the stress amplitude. How do you get cyclic loading? Obviously, vibration from rotating machinery is the big one. Pressurization cycles, so aircraft that takes off and lands is pressurized to the equivalent of 7,000 feet on the interior of the cabin, even though the exterior is much lower pressure given the plane is flying at 35,000 feet. That has led to some historically classic fatigue failures, one of which we'll discuss in today's lecture. Wind and water flow are some non-obvious sorts of cyclic loading that can definitely cause problems for structural applications. Okay, components of real vibrations. We study fatigue using usually step loading, triangular load cycles, or sinusoidal load cycles. They're easy to apply in a test fixture, they're very controllable, they're easy to study. Real vibrations are soup to nuts. They vary in amplitude and they vary in frequency. And so the first question might be, well, how in the world can we relate some regular single frequency, single amplitude sinusoidal load to what happens in the real world? The nice thing is almost any combination of real vibrations can be created by superimposing different amplitudes and frequency combinations of sinusoidal loads. So the fact that real vibrations are the sum of something that we can apply regularly in the lab gives us insight in how to study it. And in most cases we will bound any kind of unknown real vibration with a combination of what we call high cycle, meaning low amplitude, high frequency vibrations, and low cycle, which is high amplitude, low frequency. And almost all material fatigue will, its behavior will be bounded by those two cases, which we can test easily. So no, we don't aim to replicate real vibrations specifically, but we bound them with known cases that give us a range of behaviors. So test parameters that we do try to vary. We will try to impose a known mean stress. So you can think of that as sort of like a DC offset if you're comparing to electrical circuits. And so that's the sigma mean, and that can either be neutral, or it can be net compressive or net tensile. And not surprisingly, net tensile tends to be the more severe case, although that's not always. And then we'll vary the amplitude around that, again, the amplitude around the offset. And those are the two parameters we'll vary in addition to frequency. So for any given fatigue test, those will be the three parameters that you'll want to look for. Cycle frequency, how many cycles per unit time, what was the offset, what was the amplitude. From that test, we will measure the cycles to failure. So literally, you will sit there and apply a cyclic load to a material. You can use a regular universal test machine for this, or special machines that can apply cyclic loading easier. They tend to be a little bit cheaper since you're not applying huge loads. You don't always need the full capacity of a load frame to do that. And you will measure this. You will measure the cycles to failure versus stress amplitude. So obviously you have to repeat the test several times, looking for at different stress amplitudes. And so that will give you the boundary between what we call low and high cycle. So if we look at the graph that's on this slide, you have stress amplitude on on the y-axis and cycles to failure on the x-axis. Since this tends to be a lot, especially in the case of high cycle fatigue, it's usually expressed in a log scale. And for any given plot, we are looking at a specific offset. So this could have been net neutral, net compressive, net tensile, whatever. We would have a different shaped curve if it were a different offset. So if we look at the x-axis going towards that 10 to the third, we're failing the material. We're requiring a higher stress amplitude to fail the material in that lower number of cycles, the 1,000 or 10,000. That's what we'd call the low cycle fatigue end. A lot of stress amplitude per cycle, not so many cycles. Out over at the 10 to the ninth, that's the high cycle fatigue. And this would just, again, simulate different conditions of loading, any of which could be encountered in the field. And each point on that curve required a full testing to failure to produce. So this was quite a few test samples had to be machined and tested to make any one curve. Types of fatigue behavior. In terms of what we would like to see if we're designing a material, what would be very, very nice would be to have a material that displayed the behavior on the top graph, where for a given stress amplitude, if we increase the number of cycles, we would see basically a limit in the stress amplitude versus cycles to failure, such that if we stayed below that limit, it wouldn't matter how many cycles we impose, the material would never fail. That's what we call a fatigue limit. So a material that if you keep it below a certain stress amplitude, and again, this would be specific to a given offset, you know, your offset stress around which you're cycling, you don't have to worry about fatigue. And as luck would have it, the materials that tend to have fatigue limits, that have that stress below which you can cycle it forever without having a fatigue crack propagate, are body-centered cubic materials. So, of course, these are the ones that don't do quite so well in ductile to brittle transition, so there's no free lunch there. But if you don't have to worry about drastic temperature reductions in service, and you know you have cyclic loading, or you know how you have a particularly severe case of cyclic loading, you might, for instance, want to pick a steel over an aluminum, just as one case in point. Aluminum, unfortunately, being face-centered cubic, it doesn't have a fatigue limit generally. So that means that for any given stress amplitude, eventually, when you cycle it enough times, it's going to fail. So it doesn't mean you can't use it, but you have to be aware it has a finite life, no matter how low the stress is. And when these materials are used in cyclic loading, which again is almost any application, they have to be frequently inspected to make sure that we're not getting fatigue-driven cracks that could be getting close to what our K1C limit would allow for the given material's fracture toughness. So, what if you need to use a material which doesn't have a fatigue limit? This is what we were just talking about there. So here are some probability of failure curves for a very typical old aircraft aluminum alloy, a 7075, used in the T6 heat treatment, which is very strong. This has been precipitation hardened for close to maximum strength. So that's a wonderful alloy to use for lightweighting applications like aviation. So these curves all give your probability of failure for a certain number of cycles and stress amplitude. So you can see none of these curves plateaus and reaches a limit. There's no fatigue limit here. They're eventually going to fail. So if we say, for instance, we have an application where it's not reasonable to have less than, say, 10 to the 6 cycles to failure. Depending on how high our stress amplitude is, we could have a 10 all the way up to 99% probability of failure, depending on whether we had applied something close to what looks like 220 megapascals stress amplitude up to about, by 300, we are almost sure to have failed in 10 to the 6 cycles. So that just gives you an idea of how you would design. You could either design around a known number of cycles to failure or a known tolerable probability of failure, depending on how sure we want to be that we've failed. We can also look at this from the standpoint of a fracture toughness type of criteria and look at how big the cracks are, because we very likely won't fail this simply due to fatigue. We will probably grow the crack to the point where we no longer meet our safety factor for our K1C overall failure. So we will have to be watching these cracks all the time, because given that the material doesn't have a fatigue limit, we know they're growing all the time. So we will estimate the rate of crack growth, we will schedule regular inspections to assess the crack size, and then we will remove the part from service when the failure probability is low or at some point well before we have encroached on the safety factor for our K1C. Okay. Fatigue crack growth rate and stages. So fatigue cracks do not grow at the same rate during their entire lifetime. Most of the time that is spent in initiating, propagating, and growing a crack is actually spent initiating it. Once it is present as a crack, it will encounter a period of fairly regular growth that grows by a power law that you can see there in the propagation section. And then, of course, once it reaches a length for which the applied design stress exceeds, where that resultant K1, or excuse me, K applied exceeds our K1C, we'll have spontaneous failure. So initiation for a fatigue crack is when stress risers, usually from surface defects, will actually create small cracks. Again, this is the longest period in the overall fatigue life, and almost always results from surface defects. If you want to stop fatigue cracks, you stop it in the initiation stage. It's easier to stop there, and there's much more available in the way of surface modification and design changes that allow us to preclude their initiation to begin with, which has as the added benefit that we don't have to work so hard at inspecting and monitoring them. It's a very low cost, low risk, preventative approach to designing around fatigue. Things you can do there: keep surfaces smooth, prevent surface defects, harden or put the surface in compression. We'll discuss a couple of techniques to do that. If you know you have fatigue cracks, or they're already growing, or you're trying to create, say, some testing the probability of failure curves, at some point after they're initiated, the cracks will grow at a rate per unit cycle that again is described by a power law. So dAdN, A again is crack length, N is the number of cycles. So the increment of crack growth per cycle is a constant times the stress amplitude raised to a power times the existing crack length raised to another power. And we would do testing and identify those constants, and then for a similar loading scenario, the same offset and the same load amplitude, we could then predict how long it would take to grow the crack in a service situation, again provided that those conditions are the same. And again, of course, as soon as the fatigue crack length A exceeds our K1C criteria, we'll get failure. However that crack started, you'll get failure at that point. Okay, ways to keep that crack from initiating in the first place. Number one, impose a compressive surface stress. So your techniques like case hardening and other things will sometimes impart a slight compressive stress state into the surface. They will also harden the surface and make it harder to have a defect that could turn into a fatigue crack. Mechanical impact surface treatments like shot peening, to a lesser extent glass beating, will actually put the surface into a state of compression, net compression, with tensile somewhat underneath. But it's very difficult to initiate a crack when we have a net state of compression. So that's a very, very effective way of precluding initiation of fatigue cracks. And there's a little graph over on the upper right just showing the difference in surface stress state and cycles to failure in fatigue. Looking on the uppermost plot, you have a near zero or compressive stress state in the surface. That results in, for any number of cycles to failure, a much higher required stress amplitude, or for a given stress amplitude, you get a much higher number of cycles to failure. So if you think about your stress state on the surface as equating to maybe an offset in the compressive direction of your overall cyclic loading, that would be another way of thinking of how putting your surface into compression is assistive. So those are both in the direction of goodness. And of course, getting rid of stress concentrators is the other way. So that's just good from an overall design standpoint, be it yield or fracture, and certainly has a good impact on preventing fatigue. So harder surface, fewer surface defects, surface state and compression, get rid of the stress concentrators, and you will improve your fatigue life. A historical retrospective, the fatigue failure of the de Havilland Comet. This was kind of a hallmark in aviation history, and this led to an overall redesign in aircraft windows. And if you take a look at the aircraft window here, you can see that it's somewhat square-shaped, and that square shape led to a fairly significant stress concentrator, especially when put in combination with the rivets at the corner of the aircraft. And because the fuselage is round, you end up with a net hoop stress when you pressurize. So we had quite a multi-axis load from out-of-plane bending in the corner of that window as it was being sort of bent outward with the hoop stress of the fuselage, and then in the opposite direction just simply due to its shape, and then stress concentration due to the rivets and possibly a few cracks in the corners of the rivets themselves. The combination of the stress risers gave us an effective stress amplitude from cycling every time the aircraft took off and landed, and resulted in some very premature failures, some of which were quite catastrophic in the case of this aircraft. And it turned out retrospective analysis showed that when the plane first went into service after the first few takeoffs and landings, it was already well into the propagation stage of fatigue crack growth. So unfortunately, very few of these ever attained anywhere close to their design life. On the good side, it led to quite a significant redesign in aircraft windows, which has kept us all safer. So just looking at, again, the de Havilland retrospective as kind of a little lesson in design. This is an exercise that we can do with a spreadsheet. Fortunately, I will not go over that in this lecture, but it's possible this might be a homework assignment. But you can basically take the conditions under which the de Havilland was designed and used, and you can actually use modern values for K1C, and you can compare different aluminum alloys. You can literally virtually redesign your de Havilland using different Y factors for rivets and predict how it could have been designed better using our understanding of K1C and a fatigue crack propagation formula using a power law of real data for real materials. So that is certainly an exercise we can step through, again, not during this lecture, but it's an interesting way to use already existing knowledge of our materials and look at how that could have been done better. Okay, kind of moving to the opposite end of the spectrum, getting away from brittle failure. And again, fatigue is definitely a bit of an extension of brittle failure in that it just provides a cyclic loading means of increasing our A to the point, our crack length to the point where we exceed K1C. Now we're going to shift back to something that is definitely in the realm of ductile failure, and this is creep and creep rupture. So we described in the strengthening mechanisms portion of our discussions how one way to annihilate dislocations was to give them enough thermal energy to effectively diffuse upward in parallel with their own plane so that they had more mobility and could self-annihilate, could come into correspondence with an oppositely oriented dislocation. That dislocation movement, thermal movement, sort of out of plane, is also known as creep, and it is a means by which crystalline materials can undergo the same kind of viscoelastic flow that thermoplastic polymers do. So the general broad descriptor of creep is a time-dependent plastic deformation. So again, this is very similar to viscoelastic flow, and it is defined as time-dependent, again, plastic, not elastic deformation under a constant load. Stress relaxation would again be its counterpart. If we had a material and we imposed a known displacement and then looked at its load relaxation due to these types of high temperature mechanisms we'll be discussing, that would be the same kind of scenario. Failure from these mechanisms almost always occurs under a constant load and results from the material deforming in a time-dependent manner, usually to the point where it impinges on something that it wasn't designed to touch, such as a turbine blade impinging on a housing because it crept under time-dependent deformation, or it simply fails under its own weight because it's lost so much cross-section. And that is what's described as creep rupture. Material failure due to cross-sectional area loss from creep deformation. So again, creep is basically self-diffusion, movement of a material under a tensile load or a shear load. So this in metals will occur starting at as low as 1/3 to a little under 1/2 of T-melt. Obviously, the closer you get to T-melt, the faster it happens because it is a diffusion-limited process. And it can happen at almost any temperature for amorphous thermoplastics. The closer you are to glass transition for a polymer, and this includes the amorphous portion of a crystalline polymer, the more of a problem creep and creep rupture become. In fact, not only is creep a bigger issue, it becomes far less predictable as we get anywhere near glass transition. So if you're designing with polymers, be very, very sure that you include the possibility or probability of time-dependent deformation, especially if you're near glass transition. And in fact, it's generally not a good idea to design polymers to be used anywhere even close to glass transition temperature just because of this. Just find something with a higher glass transition temperature. Okay, creep mechanisms. As we touched on with metals, this is literally diffusion-enabled dislocation climb. So dislocations can move from the plane they're on, where they might be piled up against and behind other dislocations such that they can't move and the material yield is very, very high. They can climb up into another plane, move, combine, self-annihilate, and all of a sudden we went from something with a high yield that was highly strain hardened to something that might have 1/4 of the yield strength and no longer has the ability to resist yield for the design stress. So in that case, we literally changed a material in situ. Generally with creep, you at the same time will have net plastic deformation due to whatever applied load the material is under. So not only are you losing strength in terms of yield strength, you are literally deforming the material in service due to whatever load it's under in service. In addition to simply having diffusion-enabled dislocation, annihilation, and effective dislocation movement and deformation, you can drive all of the other mechanical deformation mechanisms like twinning. You can also enable complete phase changes. You're giving things temperature, so basically the applied stress that the material is under, that a metal is under in service, will apply a drive for the material to deform. Generally, this will occur by dislocation movement. You're now giving it enough temperature that things that stop dislocations moving aren't stopping them anymore. You're also providing enough thermodynamic drive to have other things happen, and twinning and phase changes are two of the things that can happen. So there are plenty of things that can happen that will enable deformation once you give the material temperature equivalent to about a third to a half of its melt point. Again, diffusion can be also described as effectively viscous flow. It's another way of macroscopically describing creep-based deformation in metals, irrespective of mechanism. We can assign effectively a creep modulus or a stress relaxation modulus to a metal, just the way we did with viscoelastic analysis of polymers. The other big thing to remember about metals when we're talking about designing a microstructure to prevent creep is that diffusion is fastest at grain boundaries. So if we're trying to prevent a metal from deforming at high temperature under the influence of surface environment stresses, we'll try to make sure that there are no grain boundaries or very few grain boundaries perpendicular to the direction of applied stress. And one of the ways we do this is with directional solidification, where we orient all of the grains, big long columnar grains, in the direction that we're going to apply stress, or we go to a complete single crystal and completely eliminate the grain boundaries. And this is possible with small parts using directional solidification, and that is in fact a routine strategy used for turbine blades, both for power generation and aircraft. So we are eliminating those diffusion freeways that allow creep to occur much more rapidly at a lower temperature. Flip side mechanism for thermoplastic polymers, creep will occur as a result of an increased rate of chain slippage. So that spaghetti pile will slip past itself a lot faster. Obviously, amorphous regions are far more affected than crystalline, mainly for the same reason that grain boundaries diffuse faster in metals. There's more open space, less chain-to-chain interaction. We can slow down the rate of creep somewhat by increasing molecular weight, but it is not a big knob to turn. It has some effect, but not a lot. Really, the only way of stopping it is to cross-link. And again, cross-linking can be strong or hard, or very strong, full covalent cross-links like sulfur vulcanization, or we can go with very strong secondary bonds like thermoplastic elastomers. The stronger the cross-link bond, the more resistant you will be to creep, especially as you get to very high temperatures approaching TG. Not, of course, that you should be using a thermoplastic anywhere close to TG. Okay, just like fatigue, we can quantify the rate of creep, so we can get some prediction of how quickly a material will fail, how tolerant we are, because everything does creep. So we can't totally preclude it, but we can design around it and see how long it will last. So if we are looking at a material that is subject to a constant stress, so again, as opposed to a constant deformation, this is the creep mode, not the stress relaxation mode. We can look at the resulting strain. How much longer is that bar going to get with time? And this is again kind of similar to that viscoelastic response. So we yank on it by applying a step load applied stress, and that's the purple vertical line. At 0 time, we jumped up to a certain stress. We're going to get an instantaneous deformation over on the right-hand side graph, and that corresponds mainly to the elastic response. And then with time at a given temperature, we'll undergo time-dependent strain that kind of can be separated into 3 different zones. Primary creep, where we have a slope that decreases with time, so the creep rate actually levels off with time. Then we're going to have a period in which the rate of deformation with time is almost constant. So we've got almost a kind of a straight line portion there in the blue. And then as we approach final creep rupture, we're going to get a strain rate that actually increases with time. And so that's usually the hallmark that we are approaching rupture. Definitely we would not want to design anything to be in service in that green part of the curve. And in fact, we would probably, if we were going to try to design a material, would want to keep down in the red area, in the portion where things are somewhat self-limiting with time. Unfortunately, any material under a given set of temperature conditions and loading conditions, it will continue to march up that curve with time. So ultimately, we need to be able to predict what it's going to do on a material and temperature basis. And here's an example of how that would work. So again, we have something loaded at a constant stress, and we are looking at the time-dependent strain or creep strain as a function of time. Total elongation is a function of time. And so we've got one material, and we're looking at the effect of either temperature or total applied stress. So if we look at the yellow curve, that would correspond to a temperature much less than T-melt, and we're seeing that we really don't approach failure at all. We just kind of have a constant strain with time. So this is a time-independent strain. That means we don't have creep at all. So that's basically room temperature type stress strain curve where there is no time dependence to speak of, very little. That would be an ideal design scenario. Not quite so salubrious is the green curve, where we have a lower, somewhat higher temperature but not very high, or a higher stress at a given temperature. And then as we increase either the temperature or the applied stress, we start moving to the steeper curves that result in actual creep rupture at a shorter and shorter time. So we definitely, if we're designing a material, we would definitely want to be staying down on that yellow curve. We might be able to tolerate something that behaves according to the green curve, but we would want to avoid anything worse than that. And again, the problem here is not simply that we will fail in a shorter time, but that we will have uncontrolled elongation or uncontrolled shape changes that could lead to failure that doesn't even require complete material failure, complete parting of the given part, the given material that we're considering. Generally, when we design around materials, we want them to stay pretty much the same size throughout their service life. So just simply having something elongate by 1 or 2% could basically render whatever part you're making unserviceable. Using material-specific test data to predict creep rate. For a given material or a given temperature, we can thankfully look up creep rate data. There are certain alloys, especially alloys that are metal alloys that are designed to be used at high temperature. All of your refractory alloys, a lot of your nickel alloys have extensive creep data because they're intended to be used in those applications. So the people who are selling them, Haynes, International Nickel, etc., will provide quite a bit of that data in order to induce you to use their alloys. So the type of data that you might find in vendor literature would look like this, where you would be shown plots of applied stress for different temperatures and steady state creep rates in a per unit time. And these will typically have different temperature regimes, obviously different slopes for different temperatures, and different slopes for different creep rates. So this is what you would design around given your maximum applied stress and your effective service time. And that is it for material failure. So this was a little bit shorter than the fracture discussion. We will pick up hopefully some portions of environmentally assisted cracking with a corrosion related lecture if that's part of this course. If not, we'll come back and treat that possibly in a class or individual exercise. The next topic after this, we will switch gears yet again and start looking back into the world of thermodynamics and in terms of phase diagrams and phase changes and preparation for microstructural transformations, heat treatment, and processing, which are all ways in which we can design materials that are stronger and better able to resist on an intrinsic basis all of these failure mechanisms that we've described here in Chapter 9. And that's Chapter 9 of the Callister text, 4th and 5th editions. Apologies, as that is changing with later editions and other texts. So we'll see you next time for phase diagrams, and thanks for a good class.